Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm Thomas Love Urban from the Texas Advanced Computing Center at the University of Texas at Austin. And I'm going to be talking about the data collection that we're putting together for NEXRAD data as part of our contribution to the TerraGrid effort that TAC is part of. You've probably heard a little bit about the TerraGrid already today, and I'm sure many of you are intimately familiar with it. Just to give a little context of that project, these are the various member institutions on it. It's essentially a large network, high bandwidth network, meant to support scientific research across the country. And initially, it had brought together essentially computational engines and sort of traditional HPC resources. With the second phase of TerraGrid, in fact, when it became TerraGrid, and institutions like TAC joined, the addition of a new kind of resource was added, that being the concept of a data collection. So in this particular case, TAC contributed 4 data collections, one of which is the NEXRAD data, the other 3 being MODIS data, satellite imagery, LiDAR elevation data, and a CT scan of fossils and geology, which Julian will be talking about tomorrow, in fact. So this particular one is NEXRAD data. As I say, this was done in conjunction with the Center for Research in Water Resources, which John used to work at before he went to Duke, and Professor David Maidment. And in addition to just being a data resource that sits out there for people to hit, this is related to our efforts under the TerraGrid Science Gateway program to develop a flood modeling gateway, which will enable hydrologists and others to go to a portal essentially and create a storm event over some area, perhaps an urban area, use the LiDAR data from our other collection, integrate that with the NEXRAD precipitation data, and run it through the map-to-map flood modeling application. And so that should be coming forth in the next couple of years. So I think we've already seen this map, or some version of this map today. This is the distribution of Doppler NEXRAD radar stations around the country, and this is where the data actually comes from initially, and it goes through a series of products as it goes from the raw data on the wire at the radars, and then sort of cascades through a series of products from level 1 to level 2 to level 3. And we are able to get this stream from the NOAA port via Unidata and collect that data. Then you can take these sort of round disks representing each of the stations and patch them together into a kind of a regular grid and convert reflectivity, because ultimately the radar is just hitting something in the air, moisture presumably, or snow, and getting back a signal, which then has to be converted into an actual estimate of precipitation, which may or may not be 100% accurate. Obviously, that's for the hydrologists, I guess, to determine. But one of the things that you can do is to take the reflectivity data and combine it with actual rain gauge point data. And so that acts as a sort of correction to the reflectivity data that you're getting back, and you can say, okay, am I off base here, or is this a reasonable number? So the combination of this reflectivity data with the stream gauge, with the rain gauge data, produces a product called stage 3. Stage 1, stage 2, and ultimately stage 3. And this is terribly confusing because you have this level 3 product and a stage 3 product, and it seems that most stage people don't know about the level people and vice versa. But at any rate, my understanding of the stage 3 is that this is a precipitation product which takes the reflectivity and correlates it with the rain gauge point data and produces a value for precipitation in a grid cell. And these are available historically, or rather the history of this data is available from the National Weather Service. For these 10, I believe there are actually a couple of more. There's Guam and Hawaii and Alaska as well. But for these so-called river forecast centers. And so we've been looking at the Western Gulf River Forecast Center for the moment, but ultimately the idea behind this collection is to collect all of the historical data for the country for all of the time that it's available, and in fact to then integrate it, and this hasn't been done yet, with the real-time data coming in that hopefully we can then, well, I'll get to that later. So yes, as I was saying, we have this level 2 and 3 near real-time data coming in. As I said, we're collecting that. The file formats are completely different from the file formats that we're using in the stage 3 data. And so there's definitely a problem around sort of integrating these two data sources, the real-time or the near real-time world with the sort of corrected historical world. So that's a whole constellation of potential problems and opportunities there. So, as I say, this collection is focusing on the historic stage 3 data for now. And the files are available as archives of 1 month's worth of data for a particular river forecast center. So it's just from a purely logistical standpoint, getting what a hydrologist will typically want to do, according to my friends at the CRWR, is, or at least may want to do in certain scenarios, is to examine a relatively small spatial area for an extended period of time, maybe on the order of years. And so to go in and unpack these files and expand them and then go, it's a logistical problem. It's inconvenient. At any rate, the monthly files are then unpacked into daily archives. The daily archives then contain the hourly files themselves, which are in a format called XMRG. And I have to admit, I don't actually know what that stands for. So these XMRG files, they're binary. They're a format that is specific to the NEXRAD community. They're approximately 300 gigabytes total for what we have so far. So not a huge amount of data, but they are fairly inconvenient for most folks in the hydrology community to decipher. There isn't a whole lot of documentation. There's no APIs out there, that sort of thing. There are issues with endianness, and the files, unfortunately, are also somewhat inconsistent in terms of the formats themselves. They'll change. A file from 1989 will be slightly different in format from a file in 2002, which is slightly different again in 2004. And those differences are different depending on which river forecast center you're talking about. So the matrix of possibilities here is really quite extensive. And so there are all these hurdles kind of standing in the way of simple and easy use by hydrologists and others of this data. And don't forget, I mean, this is the data that's already been sort of digested. It's already gone through the, yeah. Well, the data, as I say, comes from the National Weather Service. I'm not sure that that it's owned by them per se, but I mean, it's certainly not proprietary in any way. I mean, you can get the. So it's open format, but does anybody standardize it, or is anybody in charge of it? Just the National Weather Service as far. John, do you know anything on that? No. Okay. So yeah, this matrix of possible file types over the 10-year period, and I perhaps didn't mention that, it is about 10 years depending on the river forecast centers. So again, the availability of data is also inconsistent across the regions, somewhat. So let me talk a little bit about the grid that this is on, because it's not a standard grid. It's not kind of a lat long kind of thing with a certain number of kilometers for each one. A grid cell up in the north of the country might be a little bit different even in area than grid cell down below. This blue thing, this is, I believe, a county in Iowa, and the blue grid there shows this HRAP grid for which are the cells about 4 kilometers on a side that are measured for the stage 3 data. Values are given in hundredths of a millimeter. And this is kind of an interesting fact from our point of view, from a data storage point of view, and that is that on average, across time, across regions, about 95% of these cells have 0 value. In other words, no precipitation. Additionally, as you saw in the previous slide, these are sort of circular areas, and we have these square river forecast centers. Well, actually, they're not square. They're sort of based on the water sheds, but we draw a square around them to get the data that comes back is this square sort of drawn around that river forecast center. And so we also have a fair number of no data points as well, which we really don't need to store. I mean, we can kind of assume 0 if there's no data, and if there's no precipitation, and then keep track of which cells would be no data depending on the region. Yes, so while this isn't necessarily a standard kind of an open sort of standard, it is fairly understood and followed in this community. So this is kind of what one of these things looks like. Unfortunately, I don't have a map under here. One of the things that I definitely want to move into is better integration with GIS systems. In fact, that's really the basis of our architecture, which I'll get to a little bit later. But this, as you can't see, is Texas here. This is the Gulf Coast down here. New Mexico's up in this corner, and the colors, of course, show the value of the precipitation. So, as I mentioned before, there are holes in this data. There's inconsistencies in it. I'm hoping that we can possibly go back to the raw data and regenerate some of the stage 3 data to fill in the holes. I just got an email, actually, from my colleague who's working on this, and he's found even more inconsistencies and just corrupt files with bad headers and that sort of thing. So there's definitely some cleanup, which we talked about earlier, that needs to happen. I think that's one of the values of a collection like this, is that we can go through this sort of a bit of a mess and clean it up and put it in a centralized location that can then be retrieved in hopefully a fairly consistent manner. As I mentioned before, the file format has been unstable across time and across the various forecast centers. So again, a cleanup definitely needed. The nomenclature of the files themselves, so when you unpack these various archives and open them up, you can't really automate that process to the extent that one would like, or at least it's more difficult than one would like, because they've changed the names of the files and the names of the archives and so forth. So yeah, bottom line, it's difficult to use. Hydrologists will often extract this to ASCII. John showed an example of that kind of thing, where you end up with this ASCII kind of output. Data ingestion is definitely complex and quite laborious, and I think that's really the opportunity for this data collection. We can simplify the retrieval through web applications and web services in particular. The other advantage here is that you don't have this kind of artificial separation between months, hours, and river forecast centers. I mean, if you want to get a chunk of data that spans multiple files, multiple archives, it's all there. It's all in the database. If you want to get some data that spans multiple river forecast centers, again, there is no need to go to multiple sources and unpack all this stuff. It's all in the database. And then finally, we have several ideas in terms of the kinds of formats that we want to allow people to retrieve the data in. And I'll get to that a bit later. So this is kind of our setup here. We have about 2 terabytes of SATA disk, a SQL Server. This is still the old SQL Server, the current SQL Server, because we have ArcSDE sitting on top of it, and this is the Esri spatial data extensions layer. And while we aren't using this GIS server yet, we certainly want to look at making some of those geoprocessing, some of that geoprocessing functionality available as part of this web application and/or service, and then web server on top. I want to talk a little bit about the schema that we're using. This is actually a somewhat standard schema. John mentioned this earlier. We're using ArcHydro, which was developed at CRWR in conjunction with ESRI, the GIS folks. And this is really an extension to their standard sort of GIS data schema, which includes things like hydro junction, help me out here, John, hydro point, hydro this and that. And so well, I don't want to steal thunder from a later slide, but so there is, at least in the GIS context, some standard that we are subscribing to here. So theoretically, this thing, including the last 10 years of data, would have roughly 50 billion data points. Of those, because of the 95% rule, about 500 million contain actual precipitation data. The no data problem can be solved to some extent by keeping track of the masks of no data, because those are consistent. I mean, the radars aren't moving around or anything, so you have to keep track of it once for every river forecast center, and then make note of the date that the user is requesting, and then simply replicate that mask across for every time step. So that's how we can make the problem a lot smaller. So this is a slide that I got from David Maidman as well, and it just expresses this this notion that there needs to be flexibility in terms of how the data can be retrieved. So at the moment we only have one variable, right, and that's precipitation. But you can imagine water quality and evaporation and various other variables being available there, biodiversity, all sorts of things. But the idea is that when these things are in files, you're sort of limited to this kind of a query. You say, give me the entire country, or give me a river forecast center for a given hour or a given month. And it really makes it very difficult to do this kind of a query, which is give me the San Antonio River Basin for the last 10 years, or the last 2 years, or whatever. And so one of the value that we hope that the database can bring to this data collection is to allow both of these kinds of queries. And as I say at the bottom here, hopefully not this one, where they're saying give me the entire country for the last 10 years, because that's going to bog things down. But at any rate, that's one of the power of the database that we can hopefully bring to this collection. Okay. So in terms of how people would, the interfaces that people would use to access this collection, of course, web service is one. In fact, I sort of see that as the main one. We know for a fact that our colleagues at CRWR are interested in using it in this way. They usually use Visual Basic in their development, and they VisualBasic.net. And they want to be able to take this class definition, drop it into their application, into their client application, and simply invoke some simple calls to the web service and retrieve an actual object that they can then manipulate on their end. That may not be the standard mode for others. I mean, and I'll talk about that as well. Certainly, retrieving files and even ASCII text is an alternative. But this is kind of a nice, elegant sort of solution because it gives the client users some power in terms of the structure of the object. But the typical query would be a lat-longitude box. I actually should have two of those. Sorry about that. Sort of 2 points there. A start time and an end time, and then the type of format they want the thing returned in, and I'll go over those in a bit. Or they could do it by HRAP cell and then XY extent and return format. And then once we get the GIS piece in there, they could actually go in there and pick irregular basins or watersheds and then get only the cells that are associated with that particular irregular shape. So as I'm really glad that John had that slide earlier about the kinds of software that hydrologists use. Windows really is the dominant platform in that world. Certainly there is Linux in use, and especially some of the processing that I talked about, like Genpack, for example, only runs on Linux. So depending on the type of user that you are, there could be both. But Windows is certainly has a good market share in that domain, as does the Esri GIS software. As I mentioned before, would like the option of passing entire objects. The current Visual Studio web service doesn't support multi-dimensional arrays, so that's a bit of an issue. We've had to resort to arrays of arrays, which is certainly doable, but it's a little bit inconvenient and awkward in terms of the programming. OpenDAP is something we're looking at as well for multi-dimensional data. I'll talk about it a little bit in the next slide, but each of these hour-long data points or time steps has metadata associated with it. Of course, when it was collected, that's obviously necessary, but then also the name of the operator, the platform it was generated on, the maximum value across that hour, in other words, the maximum precipitation, these kinds of things. So do we need to give that with each slice, each time step? If you're doing it for 10 years, that's a fair amount of overhead. And then the collection of HRAP cells with value, meaning, for example, in the case of returning a basin, which is irregular, associating an array with each cell in that basin is also an option. So this is kind of a description of or a diagram of those three possibilities. You can kind of have a collection of time steps, each with its own metadata and its own value array. Again, a little bit heavy in terms of the amount of metadata that you're returning. Or you can have metadata for the entire query, and then a big three-dimensional chunk that returns or if it's multivariable, then it would be 4, 5, 6-dimensional. And we can't do that in the current web services, and there are concerns also there in terms of the size of that. Though ultimately it's all the same data. And then we can have the individual cells with each with an array of values associated with that, and then metadata in terms of the location of the cell and of course the time. So and then on the web application side, this is the sort of thing we envision doing. Go grab a square, same thing essentially. This could even use the web service on the back end, and then the alternative would be to select irregular basins. You just click on them, you get that basin, and then select as many as you want, and then retrieve them. So let's talk a little bit about these various formats. The thing that we were actually asked to start with was ASCII. So this is really just a text file with a little header of metadata, and then a big long list of HRAP cell IDs. So it's a 6-digit identifier, can start with a 0, identifying the HRAP cell, and then of course the value. The pro here is that it's actually commonly used, and it's simple for users to deal with. They don't have to know how to read binary files and that sort of thing. Of course, it's quite inefficient as well. As I talked about before, .NET objects can hand those around. Obviously, not particularly handy for people who aren't programming on .NET, or who can't get the client code for whatever reason, or don't want to. We can repackage essentially the data that came in into the appropriate shape and return an XMRG file right back, just in the correct with the correct data that they want, and then NetCDF is that's an open standard that we can use. It's actually fairly similar to the XMRG format in that you have a header and then blocks of data, and then for each time step you'd have an additional block. And then finally, for the GIS users, what actually seems to be the most convenient is an actual geodatabase. So we would actually return an MDB access database file with the data, and also data about the various cells. So each cell would be an object or a record in that database with its unique identifier. And this can just plug directly into a GIS model. So that's the convenient thing there. In fact, that's probably where we're going next, just because that's what our users are asking for. So future plans on this. First of all, we have to get all the data in there. Right now, as I mentioned, we're only dealing with one river forecast center, the Western Gulf. We need to load in the rest of that, clean it up, hopefully fill in some of the holes that we have, and get that going. But then after that, we'd like to add variables. So that third dimension that I showed earlier. Yeah. Yeah, that's well, so again, in the TeraGrid context where you have all this bandwidth to use, and you want to be able to, one of the projects that this is also associated with, which I didn't actually mention, is a project that Microsoft is sponsoring to look at using relational databases in a scientific context. And one of the things that we would definitely want to look at in the context of that project is running SQL Server on a cluster and having direct I/O from the various nodes in the cluster to a compute node, for example. So, yes, not specifically in terms of this collection, but in the broader context of things, yes, we are looking at essentially parallel I/O from database clusters. Okay, so yeah, so some of the additional data, gauge point data, so rain gauges and stream gauges, water quality. And then another thing that's of quite a bit of interest is integrating this data with other collections that are available via web services in a seamless sort of manner. So you can come here, make a request for 8 variables. We might provide 1 or 2 or 3 of those, and then the service would go out and aggregate the data from 6 other web services and provide it in some, hopefully, cohesive manner. And then, as I said at the beginning, we'd like to integrate the real-time data feeds, and there are already some applications that we've identified in terms of where this can be an input to another application sitting on top of it and extending the GIS integration functionality. Just wanted to run real quick a little demo of an application we built. This is actually sort of this is a desktop application that we built as our central location for inputting the data, for ingesting the data, and for kind of taking it out again. So normally I would be doing this from a database. Since I don't have SQL Server on this laptop, I'm going to go to Files. And I'm grabbing a number of hours. There's about 24 hours worth of data. Just so you can see a little bit of how this particular thing, this is from June in the Western Gulf, so that same area from the Gulf of Mexico up through to New Mexico. So you can see here, it's a nice little meteorology thing. And that's it. Any questions? Thank you.